downloaded some book from an online bookstore, or it may be the last album of your favorite music band. Now you have this book, or the album, on the hard drive of your computer, and you are the happy owner of it. But what happens with this item in the online store? Does it stay there, or it disappears after you downloaded it? Well, for most of us nowadays, this question even looks stupid. Of course it stays there, because what you have downloaded is just a copy. And you may create as many copies of classical digital data as you want. It is a very important property of classical digital data. We don't even notice how often it is being copied. Even when you read your digital book, it is copied several times inside your computer, from hard drive to physical memory, then to the memory of your GPU, etc. And it goes back to the hard drive each time your computer decides to swap it and to release its physical memory for something else. Now imagine that some very innovative bookstore starts selling quantum books, meaning that the data of this book is encoded as a state of some large enough quantum system. Can you download such a book? What happens to it in the bookstore when you download it? Well, maybe this analogy is not very good, since first you have to decide how to transfer quantum states over the classical channels. But imagine you can. The question is, can you copy quantum data? That is the state of a quantum system. Before we can answer this question, let's take a closer look on what does it mean to copy something. Making a copy is very close to making an observation. When you observe a text, you make a copy of it inside of your brain. And when you copy text from one computer to another, it is like the second computer has observed the text stored by the first computer. And we remember, I hope, that observation is a very sensible process in quantum mechanics. Observation alters the system for us. And I'm pretty sure that this imaginary quantum bookstore wouldn't agree if its products will be altered by the customers. So, is there a way to copy the state of a system without touching it? Okay, honestly, sometimes there is. If you know the state of the system, for example, we created this state, then it is possible to create it once more. But in this case, it is not exactly copying of quantum data. It is more like following the recipe for the state creation, but the recipe itself is classical. However, if we don't know the quantum state, and when there is no classical recipe to reproduce it, the situation becomes worse. We can't read quantum states without altering them. We learned this on the previous weeks. But maybe we can transmit this state to another quantum system without destroying it. We ourselves won't observe it. Let the other quantum system observe it for us. In the previous week, we learned that evolution of a quantum system is unitary. It means that the state of a quantum system is transformed as if it is modified by some unitary operator. In our case, there are two systems. First, represented by a vector phi, is the state of our interest, the state that we want to copy. And the second, represented by ket psi, is the recipient system, the system which will receive the copy of phi. Now, these two states are transferred to some quantum copier, which does all the magic for us, such as after it we have two systems in the state phi, and no psi anymore. Looks good, right? Wrong. It looks completely wrong. And the strongest symptom of the fallacy is disappearing of this state, psi. It does not contribute to the result. And if we pass different states, psi1 and psi2, as the second input of our magic copier, the result stays the same. It means that the transform implemented by the copier glues up together different states, and it is not unitary. And not unitary transforms are not allowed by quantum mechanics. We discussed this on the previous week, which means this kind of device, the quantum copier, cannot exist. This result, the impossibility of copying of an unknown quantum state, is known as the no-cloning theorem. The theorem was formulated and proved independently by James Park, Wouters and Zurich, and by Dijks in earlier 80s. By the way, I want you to remember this kind of reasoning. If you doubt the possibility of some procedure in quantum mechanics, the first thing to check is the unitarity of this procedure. Now let's consider the following scheme. You can notice that in this case, the state psi is not destroyed, but there's no copying of the state phi either. This procedure, the swapping of the states, is indeed unitary and thus possible. It is even possible if these two systems are very far from each other. However, it is useless for our imaginary quantum data online store, since it does not allow to sell many copies of the data. The quantum state transfer in this case, when the physical systems don't interact with each other, is called the teleportation of a quantum state. This will be the topic of our next lessons. The impossibility of copying of an unknown quantum state is a serious obstacle for many things we would like to do with quantum data. But it is not the first time when such obstacle itself becomes a very useful resource. Classical cryptography uses practically undecidable tasks in its asymmetric algorithms. And so the quantum cryptography does with the no-cloning theorem. We will discuss some quantum cryptography algorithms very soon in this module.